Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. This is subsection 4.3.7. We're going to be looking for a subgroup that looks like um, this group right here, mod 4 arithmetic, inside of the group of permutations and four things. Okay, let's go for it. So the group of permutations and four things has 4 times 3 times 2 times 1. So 4 factorial different permutations in it. So it's a bigger group. And if you only have a set of four things or subgroup of four things, it's going to be a subgroup if we can find it in there. So we're going to do that by investigating permutations on between vertices on a directed graph, directed meaning, so this is a graph, which means there's vertices and edges. That's what graph means in this context. And the edges are directed, all right? And it's going to preserve that structure. So how do you preserve a structure like that? You're going to preserve an arrow structure. So meaning that in particular, so if you have 1, 2 in your domain, 1 to 2, then in your codomain, what is it going to output? So 1 is going to go to somewhere, and 2 is going to go to somewhere such that there's an arrow between their images. So there's not many options. So 1 and 2, this arrow with 1 and 2 has to go to like here, or to there, or to there, or to itself. In fact, there's 4 options, here, 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 and here. And in each option, it actually determines where everything else should go, because where 2 goes determines where 3 will go, right? Because that's an arrow too that needs to move. And if 2 is going somewhere, then 3 might go somewhere. Now, if 3 goes somewhere, that determines where 4 goes. And where 4 goes, I mean, everything's determined by just where one arrow goes. And so you get 4 different types of permutations that actually work. These are rotation. These are rotation permutations. So basically in the reading, everything that's discussed here just kind of goes through that idea. And here are the 4 options right here. Okay, so we have this subgroup, and we can write it out here where we take this guy and then compose it with that guy. So in writing, this will come left on the left side, this will come on the right side as we write it down. Okay, so we have a subgroup. We could write it out this way. Now, okay, and it's the exact same as this. If you take a look at this and do a crossing over, if identity, you replace it with 0. This guy 1, 4, 3, 2 with 1 bar here, and so 1, 2, 3, 4 is what I meant to say. Yeah. Oh, that's what I wanted. 1, 2, 3, 4. Okay, 1, 2, 3, 4, going with 1 bar. 1, 3, 2, 4 going with 2, and 1, 4, 3, 2 going with 3. And honestly, those could be flip-flopped somehow. But nonetheless, we do get a group. Yes, it's right here. Here's the table here describing that, and the group tables look the same. This means that the subgroup that we found of permutations and Z mod 4Z, they're isomorphic. This is a bijection, and it preserves structure. So a bijection that preserves the structure, the group structure that we want, is called an isomorphism. So if you have a function between 2 different groups and it preserves structure, how do you know if it preserves structure? Basically, if it just preserves the operation of the groups. Because if you're preserving the operation of the groups, you're going to the operation itself and preserving everything with it actually preserves identities and inverses and everything else, just by virtue of being a function along with the preservation of the operation. So really, if you want to show that structure is preserved for groups, you just got to show that the operation is preserved, really, that it just transfers nicely, that if you do it before the operation before or the operation after, it's the same. That's really all you need to do. And then as long as it's a bijection, you have an isomorphism between groups. It's kind of a nice feature here. There's not much to check to show that something's an isomorphism. Okay, so so this is the notation that we use for isomorphic. Okay, All right, so let's take a look at this, where we're going from here. Okay, we're going to be building up a group in a subgroup of S4, and we're going to give a name for this permutation, 1, 2, 3, 4, R. It means to rotate things once around counterclockwise. Do one counterclockwise rotation. This will mean to go twice around. This is 3 times around, and the identity R to the fourth is just about to stay put. Um, so, okay, so the exponent just means how many times we repeated the composition, really. So this is a composition exponent. Keep that in mind as we go forward. Okay, so, and we have this. So we could actually do our compositions and think of them as addition in mod 4 if we wanted to. That's just another way of thinking about it, because that's what this is referring to. So for instance, in fact, the exponents themselves give you a nice isomorphism between mod 4 arithmetic and an addition and the composition. So 7, you could think of that as 7 bar, and 6 bar. So you add those, and you get 1 bar, so R. So that's just another way of working with the exponents with the composition. You can just automatically just transfer to mod 4 arithmetic by just looking at the exponents. Okay, and we'll conclude this this little video. Thanks for watching.